Let's take one more look at finding areas of regions bounded by curves. And on this particular example, I've grabbed a graph that I had in Desmos, and let's find the area of the region that is highlighted below on this graph. And it is bounded by the two lines, x equals y and x equals 2 minus y, and then the parabola x equals y squared minus 2y. And there are actually a couple of regions bounded by, three different regions bounded by these three curves, but specifically, let's take a look at the region bounded where y is between 0 and 2 and highlighted below. So we can see that little region right in there. Now, when I look at this, and given the way these functions are defined, x as functions of y, I would say we're thinking about a horizontal orientation. So how are we going to do these curves with a horizontal orientation? Well, let's think about what a representative rectangle would look like so we can determine which is the function on the right, because if we're doing a horizontal orientation for finding areas, let's remember that our formula says we find the area by integrating from c to d of f of y minus g of y dy, just reiterating the formula we derived in the last video. So that's integral of the function on the right minus the function on the left with respect to y. So remember when we talk about those function on the right, because this is where f of y is greater than or equal to g of y on the interval for y from c to d. Okay, but this is where things get a little bit tricky on this particular picture, because take a look at this first rectangle that we have right there versus the rectangle we have right here when the graph, notice on the right, switches from being the red line, x equals y, to, these are both functions on the right, but notice, I'm going to change my color here, notice that this is the function on the left. The parabola is the function on the left for both of those rectangles, but notice that the function on the right switches halfway through that region, it switches to a different line. And so right in here, I'll draw a little line kind of through there. Let's do it in black actually so it stands out a little more. Right there, and I kind of did a squiggly line so it would stand out on our picture. Notice that right there, our region is actually changing. Our region is changing from x equals y being the function on the right to x equals 2 minus y being the function on the right. So in order to do that, I have to think about what that means in terms of my graph. Now, there is some symmetry in this graph, and that's simply because the slope of both of those lines they're equal and opposite, and the parabola that we're looking at on the left is also symmetric because the cut point there is at the vertex. But it wouldn't matter. When we set these up, whether it's if it's symmetric, we can use some other techniques. But if it's not symmetric, we have to split this up. We have to think about what's happening on the left, what's happening on the right when we're setting up these areas. So let's come back in here. I'm going to erase my two little rectangles right there for a second. Oh, I erased my highlighter too. So let's come back in here and let's think about how I set this up. Well, I have to set it up. I have to break this integral up into two parts. And even though they are symmetric because of the specific functions we're working with, let's set this up as we would even if they weren't symmetric. So the area, the total area of the region, is going to be equal to the sum of 1 plus 2. So how do we find the area of the first region? Well, the area of the first region is from 0 to 1 on the y-axis. I covered up 1, but this is that is 1 right there. This is 2. Now the lines are the lines I drew kind of went right over the values on the y-axis. But from 0 to 1, the function on the right minus the function on the left. With respect to y, well, that's from 0 to 1. The function on the right on that region is y minus the function on the left is y squared minus 2y dy. And the area of the second region, also a horizontal orientation, when we draw our rectangles on that region, we're integrating from 1 to 2. And the function on the right on that region is the line 2 minus y, and the function on the left is the parabola y squared minus 2y dy. So when we're setting that up, we're adding those two areas together because they have to be calculated differently, separately, because the function on the right changed from one region to the next region. So we had to set those up as two separate integrals. Now, this part of the calculation is going to be just a little bit of algebra to simplify, and then application of our basic rules of integration. So I'm going to speed up the video and do that calculation, and let's see what we get here for those two, the sum of those two areas, so the sum of the total. Okay, and there we have it. So our area, after we do the computation, add those two areas together, our total area of this region is 2 1/3 units squared, or 7/3 units squared. And you can see what I was doing right there was adding up those two regions of area. So this is region 1. This was the integral to calculate region 1. This was the integral to calculate region 2. Added them up and we get to this answer. I just wanted to mention, I talked at the very beginning about how there was symmetry and we could have done this with symmetry. And so if I come in here and I look again, because of the symmetry of this particular graph, it turns out that 1 is actually equal to 2 in this case because of symmetry. And so if we focus in on just the calculation of 1 here, if we follow this down and we focus in on the calculation of the area of 1 right there, notice that we find that area 1 is actually equal to, let's see, I don't think I actually have that. I simplified a little differently in my work there. But that's negative 1/3 plus 3/2, which when we add those, we actually end up getting 7/6 when I add that, because I get negative 2/6 plus 9/6. So I get 7/6 right there. And so by symmetry, we could say, well, 1 plus 2 has to be equal to 7/6 plus 7/6 because they're symmetric. And we end up with 14/6, and that reduces to 7/3. And so just notice that by symmetry, because of the symmetric nature of these, just kind of a little thought bubble on these, thinking about the fact that these were symmetric. This is another way to think of this, and it was because of the symmetry. Obviously, if these were not symmetric regions, we'd have to calculate each of the areas and just add them up. But here's another way to utilize symmetry if we happen to notice it, right? If we had thought about the symmetry and the fact that those two lines were had equal and opposite slopes, and we were symmetric right at the vertex of that parabola, we could have actually utilized symmetry here too. But either way, when you have regions where you've got multiple curves, more than just two curves bounding the regions, you can divide it up and calculate the areas individually and then add them up as we did here. Let me get the whole example on the screen here in case you want to take a screenshot of that and add it to your notes.